So I have some code here in an online compiler, a C++ compiler, to estimate the yield to maturity of a bond using, again, it's C++. And basically the function can be subdivided into two sections. One where we have, as before, a way of estimating using a loop structure the present value of a bond. And then in the second part of the code, we invoke this PVB function to estimate the PVB again. So we invoke the code up here, present value of bond function, where we discern the face, the coupon rate, the discount rate, the periodicity of the coupon payment, and the maturity of the bond. That's invoked and is used. That function is called here. And then in a bisection function, we then go on and estimate the yield to maturity. So typically, bond data is presented as, we know the face value of the bond, we know the coupon rate because that's typically given. The target price, or the target, if you like, could be viewed as the market price of the bond. So that's normally directly observable in auction type conditions or in secondary market type conditions where the bond price is reported. We've the maturity of the bond, we have the frequency of the payment of the coupon, and then we have the low ball and high ball guess for what the yield to maturity. 10 here, however, would denote absolutely 100%, so 1000%, which is way out of whack. 1 here would be 100%, 10 is 1000%, and then this value here is also equally implausible. But these are, if you like, initial seed values that we use to seed the bisection function, and then we triangulate, or we define a level of tolerance between which those two values eventually equate. And once we have reached this target level of difference, that might be a little bit small, we will reduce it. Then when we run this function, we can estimate the yield to maturity, or the internal rate of return on the bond. So let's run that and see, is the bond function actually working? And we're getting this value 559987. Now we can compare against the actual. Let's look at those parameters and see, is that consistent? Is yield to maturity consistent with 5.6? So here, for instance, is an example where we went in the other direction, where we actually knew the face value, the coupon rate, the discount rate, and the time period, and the frequency of the compounding is twice a year. And to estimate the present value of the bond, if we input it, if we discounted the coupon using a present value of annuity structure, discounted the face value of the bond, the present value of the bond would be 1010.91. If we go the opposite direction and we know the bond price, we know the coupon rate is 0.06, the face is 1000, the time to maturity is 3 years. If we wanted to deduce the interest rate consistent with this market price if reported, and we're trying to determine the discount rate, then we would use the bisection function. We can see here, using the parameters that we have here, which are consistent with the parameters that we have here, so 1000 face, coupon rate 6, 1010, 91 is the market price, t is equal to 3, periodicity of the coupon payment twice a year. When we run this code, we can observe that the value reported for the yield to maturity is 5599, so virtually 56, and that value is consistent with the value we had seen initially. So I'll just that's consistent with this discount rate that we observe here. So the model the model output, the C++ output, is consistent with the discount rate, and that should provide some evidence that the bisection function that we've defined is working. I'll leave a link, so if I go back into the online compiler here, I will leave a link to this code. Maybe we can do one more check before I do that. So here's another example, perhaps a little bit better in terms of, it's more intuitive in terms of what we're trying to demonstrate. We've a bond price trading for 1,010.77. We have a coupon rate of 6%. We don't know the discount rate on the bond. We want to determine that value. It should be 5.6%, but that's the value we want to verify. Okay, so that's something we can check. The face value we said was 1,000. The coupon rate was 6% in that case. I forget this value. I think it's 1,010.77. So delete 1,010.77 is the market price. We'll check that in a second. 3-year maturity. Frequency of the coupon payment is once a year, so we delete that. Put in 1, and then again the same idea, low ball, high ball guess. So let's just check our initial numbers. Okay, so the market value, the face value is 1,000, the market price 1,010.77, and we want to know this value. We want to verify that the discount rate is 5.6%. Okay, so the target value is 1,010.77. Let's just run this and see what results we obtain, and we should get close to 5.6%. Okay, and we get a little bit higher. Now, can we make that more accurate? We could come up here to the tolerance level and put in a few more zeros. That would mean a few additional loops. Now, the more zeros we put in here, the more estimation and runtime is going to be gobbled up, but let's just run that. It will take longer. 5, 6. We're still stuck here around the same number. Let's put in a few more zeros to see will that clear that up. And one more time. Probably won't do anything, but will take longer. And I think we've probably gone as far as we can go here in terms of the level of accuracy. So 5.6% and a bit, okay, is the estimate that we have for yield to maturity. Okay, and also just to note, I will share that code, so I will make a note of this link, copy this link and leave it below the video clip in YouTube.